So now this video discusses about the real life applications of the equations of kinematics. But before we go further with the applications, let's just have to remind each other about the equations of kinematics and the principles behind. We understand that we have 5 equations of kinematics. We have the first equation, which is for the average velocity. We have it as the average velocity is equal to the initial velocity plus the final velocity divided by 2. And we have another one, which is for the average displacement. We have the displacement is equal to u plus v divided by 2, and that times time. And we have another formula for the acceleration, which is acceleration is equal to v minus u divided by, should be that 2, should be divided by t. And of which, if we think of making v as a substitute formula, we'll have the final velocity being given as at plus u. And we have the fourth equation, which is the displacement is equal to ut plus half at square. And the fifth equation is given as the v square is equal to u square plus 2as. So in the first equation, if we have the initial velocity of the object and the final velocity, we can be able to have the average velocity using that formula. And then the second equation, if we have the time takes and if we have the average speed, we can be able to have the average displacement using the formula as well. Likewise, if we have the time takes, final velocity, initial velocity, can be able to have the average displacement in the same way. And also in the same case, if we have the displacement, initial velocity, final, we can be able to have the time using the same way. And on the second case, if we have the final velocity, initial velocity as the time, we can be able to have the acceleration. Likewise, you can also be able to have the final velocity if we have the acceleration time as the initial velocity. In the fourth equation, if we have the initial velocity time takes as well as the acceleration, we can be able to have the displacement. And likewise, if we have the displacement, if we have the time takes as well as the initial velocity, we can be able to have the acceleration using the formula as well. And also in the other case, on the fifth equation, if we have the final velocity, initial velocity, acceleration, we can be able to have the displacement using the formula. And also, if we have the displacement, acceleration, initial velocity, we can be able to have the final velocity in the same way. So just have to understand how these equations are basically being used in a typical problems. And of course, in case you are not much aware about the working principles actually behind these formulas in a typical problem, so just have to post the link in the comment section below where you come across the video I explained about the derivation of these equations and how you can apply them in a different problems. So keep that in mind. Now the point of interest in the video is to discuss about the real life applications of these equations, and basically we'll be looking at what we call as the chasing problems, where the two objects are chasing each other, and also we'll be looking at what we call as the head-on case, where we have two objects going towards each other, and also be looking at what we call as the racing case, where the two objects are starting from the same position until they overtake each other. Those are the typical applications you should have to understand about the equations of kinematics and in real life situations. But before we proceed in the typical applications, let's try to conceptualize much about the displacement formula. So we understand that the displacement formula basically that will be used in the analysis is given as S is equal to ut plus half at square. Basically, this is the formula that will be used much in the analysis. So why this formula will be highly used in the analysis is because it is composed of all components to do with motion. You know, the formula contains the displacement, the formula contains the velocity, the formula contains the time, as well as the acceleration. Hence, this is the best actually formula to be used in the analysis of our discussions, basically in the typical applications of the equations of kinematics in a real life situation. So we understand that whenever an object is moving from rest, initial velocity is given as L, and that is for the object which starts moving from rest. If that is the case, it means according to the displacement formula, we'll have the displacement is equal to 0 times t and plus half AD square. In that case, the displacement formula will be given as 0 plus half AD square. That will be given as the displacement is equal to half AD square. And this is how the equation will be used whenever the object starts from rest. So no wonder you just have to see basically this displacement equation being expressed as this whenever the object starts from rest. And this is how it will be for the object starts from rest. So for the object starts from rest, actually I should have this, by the way. So for the object starts from rest. So this is how the formula will be used, because the initial velocity is L, the whole of this one will be given as L. So keep that in mind. And that is for the object that is starts from rest. Let me put it here. And for the sake of interest, so have it as the displacement is equal to, let me have this, displacement is equal to, or have the displacement is equal to half AD squared. This is how it will be for the object which starts from rest, where the initial velocity is 0. And now how about if the object is moving at a constant speed? So as we discussed already this last time, we said the object which is moving at a constant speed, acceleration is always 0, and for the object moving at a constant speed. So what is this? Now using the displacement formula, you know, displacement will be given as ut plus half times 0 times t square, of which you have the displacement being given as ut plus L. This is the same as the displacement is equal to ut. And this is how it will be if the object is moving at a constant, actually at the constant speed, where the acceleration is L. So it's either you can have the displacement being given as ut, let me just have this. You know, it is the same as having it as the displacement being given as Vt, because if the object is moving at a constant actual speed, it means the initial velocity is the same as the final velocity. Hence, we commonly use the displacement formula being expressed as this, where this corresponds to the speed, which is the constant speed in which the object is moving with. So this is how the displacement formula will be expressed if the object is moving at a constant speed. So displacement will be given as Vt, where acceleration is 0 because the object is moving at a constant speed. So you need to understand about the actually in that case. So whenever the object starts from rest, then the displacement formula will be given as this, since the initial velocity is 0. And whenever the object is moving at constant speed, it means the acceleration will be given as 0. Hence, the displacement formula will be given as Vt. So take note of that. So let's now go into the analysis of the typical applications of the equations of kinematics in a real life situation. We have the first application, which is said to be actually head-on case. What is head-on? We have what we call as the head-on case. So in this case, the point of interest is that, let's say if we have two objects, let's say this is our object, I'll say the one, and let's say it is moving towards this direction. And let's say the object starts from rest, where initial velocity is 0, if that is the case. And let's say it is moving at a constant acceleration, which is given as 4 meters per second square. And let's say ahead of it, there is another object, let's say, which is moving. Let's say there is another object which is moving towards the opposite direction. Let me have this. You know, we have the object 1 moving towards this direction and the object 2 moving towards the opposite direction. Let's say it is given as that. And let's say the object 2 is having also initial velocity given as 0, and it is moving at a constant acceleration of, let's say, 6 meters per second square. And let's say the two objects are far away from each other, about 20 meters. Now the point of interest is, where will the two objects meet, if that is the case, and after how long each has to travel before they meet? So that's the point of interest. This is what we call it as the head-on case, where the objects are approaching towards each other. So how do you think we should have to analyze this case? So first thing you should have to understand is, do we know the time it takes for the object 1 to travel to meet object 2? The time is unknown. And how about the distance object 1 has to travel, symbolized as S1, to meet object 2? It is unknown. And do we know the time takes for the object 2 to travel to meet object 1? We don't know. And do we know the distance the object 2 has to travel, which is to be symbolized as S2, to meet object 1? It is unknown. But now, using the displacement formula, which is given as, you know, AC is equal to UT plus half AD square. So let's think of substituting these parameters into the equation. Now you understand that the displacement for object 1, which is given as S1, will be given as, you know, we have the initial velocity, which is given as 0. Hence we'll have it as half, and the times acceleration, which is given as 4 times t squared, since time is unknown. So we have the displacement S1, which is equal to 2t squared. So this is equation number 1, like that. And how about the displacement for object 2? We'll have it as S2. Since the initial velocity is given as 0, we'll have it as half times 6 and the times t squared, of which we'll have it as S2, which is given as 3t squared. And this is given as equation 2. So keep that in mind. And from there, you start to understand that. Actually, these two objects, they'll have to share 20 meters, because as you can see here, this object, the fact that it is moving fast, since it is having the large acceleration, it will cover more distance than this object. And the fact that they'll meet at the center, or the fact that they'll meet within the space, you know, the distances traveled by each object, if we think of summing them up, will be equal to 20 meters, because both objects will share the same separation distance, no matter what. The fact that both will meet within the separation distance, you understand that the distance traveled by this object plus this object will be equal to the separation distance. If that is the case, then this is true. You know, S1 plus S2 will be equal to 20 meters. And since both will share 20 meters, you know, the point of interest is that it is like that you have a friend. Let me have this. for you to clearly understand what's the principle behind that. You know, the point of interest is that you have a friend. Let's say this is your friend, like this, and now this is you, like that, and you are moving towards one another, like this. And let's say the separation distance between you is given as 10 meters. So no matter whether one of you will move fast or not, but if we have the summation of your respective distances, won't exceed 10 meters, because you all have to share the same distance. Hence, that's the way to analyze that one. So if that is the case, since S2 plus S1 is equal to 20, then we have to substitute for S1. S1 is given as 2d square. In the plus, we have for 3d square, which is equal to 20. Then having the like terms, we'll have it as 5d square, which is equal to 20. And dividing both sides by 5, we have d square, which is equal to 4. Therefore, the time takes will be given as 2 seconds. So which means each object has to travel about 2 seconds actually before they meet at whichever the point within the space. So this is the distance, actually this is the time takes for the object 1 to travel, you know, to meet object 2, and also this is the time takes for the object 2 to meet object 1 at the center. So keep that in mind. And how about the distances they have to travel in each case? So the distance in which the object 1 has to travel, we'll now have to substitute into the equation for distance for object 1. That is S1 will be given as 2 times 2 to the power 2. That will be given as 8 meters. So which means object 1 has to travel about 8 meters to meet object 2. And likewise object 2 has to travel about 3 times 2 to the power 2. You know, 2 to the power 2, that will be given as you know, S2, that will be given as, we have it as 12 meters. So it is really true that the object 2 has to travel far much away than actually object 1, because it is having large acceleration. Hence, it will cover more distance than object 1. So this is how you should have it. So how about their final velocities at the point in which they will have to meet? So in order to have the final velocity in which object 1 will have as it to meet object 2, we may think of using the fact that we have the now initial velocity actually being given as 0, and the acceleration we said is given as 4 meters per second square, and now we have the time which is 2 seconds, and we have the displacement which is being given as 8 meters. Now we can be able to have the final velocity actually for the object 1 as it will meet object 2, using whichever the equation of kinematics that we discussed recently. So think of which equation should we use, and also in the same way, what is the final velocity of the object 2 as it will meet object 1. Also principle means the same. So we have the acceleration which is 6 meters per second square. We have the time takes which is 2 seconds. Both will have the same time. And we have the distance which is 12 meters. Then now we can be able to have its final velocity as it will meet object 2. Rather as it will meet object 1. So that's the principle behind that one. Now what if we have the one object moving at a constant speed? Let's say one object is moving at a constant speed, and are using the same case which is the head-on. Let's say one object is moving at constant speed. Let's say we have object 1 is having the initial velocity which is given as 2 meters per second. let's say it is accelerating at a constant rate of 2 meters per second square. And let's say object 2 is moving at a constant speed of, let's say, 20 meters per second. It should be 4 meters per second. So how do you think we should have to analyze this one? You know, principle remains the same in the sense that we don't know the time takes for the object 1 to travel. We also don't know about the distance it has to travel to meet object 2. And the fact that this one is moving at a constant speed, mind you, it means acceleration is given as L. And in this case, we don't know the time it takes to meet object 1 and also the distance it has to travel, we don't know. But the rate is that what is distance S1, we'll have it as, now using the displacement formula, which is AC is equal to UT plus half AD square. We'll have to substitute for U, which is given as 2, now half 2D. And plus C, acceleration is given as 2, and 2 divided by 2, that is being given as 1, so half D square. This is equation 1. And how about the displacement for object actually 2? Now since it is moving at a constant speed, mind you, AC actually 2, if it is moving at a constant speed, it means the acceleration is L. Hence we say that the displacement formula will be given as Vt. Hence S2 is given as 40. This is equation number 2. And from there we can be able to have the time takes using the same principle, in the sense that we'll have S1 plus S2, which is given as 20. And for that case, then we can have, you know, that one as we have it as 2D plus D square and plus 40, which is equal to 20. Now since these are the like terms, we'll have it as D square plus, should be 60. Now what we have is should be 60. So in this case, minus 20 is equal to 0. Now what we have is the quadratic equation, of which let me just have to keep the equations S1 as well as these two somewhere. So we have S1, which is 2D plus D square, and S2 has to be kept on the same point. We have it as 40. So let us see if the factor method works in order to solve 40. Will the factor method work? So in this case, the factor method will not work. Hence, we just have to use the quadratic formula, in the sense that we have A, which is given as 1, B is given as 6, and C is given as negative 20. And what is the quadratic formula? We'll have it as D is equal to negative B plus or minus square root of B square minus 4AC divided by 2A. We'll have that and as that. And from there, you just have to substitute the values of A, B as well as the C. So time will be given as, what is B? We have it as, now have 6 plus or minus square root of, now what is 6 to the power 2? We have it as 36 minus, now we have 4 times 1, that is A, and times negative should be 20, that is positive 100. That is positive 100 divided by 2 times 1, that is 2. And that one will be given as, now in this case, we can have it as the time is equal to negative 6 plus or minus, now we have 136, which is divided by 2. We'll have that and as that. And hence we can have it as, what is the square root of 136? So the square root of 136. So what would be that? So what's the square root of 136? So square root of 136, that is 11.7. So we have negative 6 plus or minus 11.7, that is divided by 2. Now, since the time can't be negative, we'll just have to go for the positive actually time. Hence, we'll have it as, that should be about negative 6 plus 11.7 divided by 2. And 11.7 minus 6, that is 5.7 divided by 2. We'll have it as 2.8. So the time takes is given as 2.8 seconds. So each object has to travel about 2.8 seconds to meet somewhere. And how about the distance each object has to travel? Now the distance in which each object has to travel will be calculated upon substituting the distance, upon substituting time, and for the distance object 1 as well as the object 2. And from there you can also be able to have the final speed for object 1 as it will meet object 2. So try to have that one, and in case you are having difficulties, I want to see the responses in the comment section below in case you are having difficulties. Now what if we have, this is the case, what if both objects are moving with the constant speed? What did you say? What if both objects are moving at a constant speed? What did you say about that? Let's say object 1 is moving at a constant speed which is given as 12 meters per second. And the object 2 is also moving at a constant speed which is given as 10 meters per second. You know, where will the two objects meet and after how long? You know, principle remains the same. Since both are moving at constant speed, we don't know the time takes each has to travel, of course, like that, we don't know. And how about the distances each has to travel? We don't know, like that. Should be that. But what is S1? We'll have it as 12t. This is equation 1. How about S2? We'll have it as 10t. That is, and also keep in mind that 12t plus 10t will be equal to 20. Then you can be able to have the time takes in the sense that we'll have it as, you know, 22t is equal to 20. Then we'll be able to solve time. You'll be able to solve for time, and afterwards you substitute and find their respective distances. As simple as that. And now try to complete this one at your own time. And I want to see the responses in the comment section below in case you are having it right. What if we have the two objects? Let's say this is object A moving towards this direction, and with initial velocity given as 5 meters, and also the acceleration given as 5 meters per second square. Let's say that is the case. And we have the another object that are called as the object B. You know, happens to move in the other way direction. Let's say this is object B, and the separation distance is given as 100 meters. And let's say it's having the initial velocity given as 4 meters per second. Let's say the acceleration is given as 3 meters per second square. What is the distance each object has to travel, and also the time takes for each object to meet somewhere, and also their respective final velocities? So try to have that one. And what is the another application you should have to understand? So the another one is what we call as the racing case. That is application B. We call it as the racing case. So what is this? So let's say we have two objects. Let's say this is object 1, and that is moving towards this direction. and say it is having initial velocity given as L, and let's say it is moving at a constant rate of, let's say, 4 meters per second square. And let's say on the same position and adjacent to the object 1, we have an object 2, which also happens to move in the same direction. But now this object, and let's say it is moving at a constant speed, let's say given as should be 12 meters per second. Let's say that is the case. Where will the two objects overtake each other, and after how long? So that's the point of interest. So principle remains the same. Do we know the time takes for the object 1 to travel? We don't know. How about the distance for object 1? We don't know. But the displacement for object 1 will be given as S1 is equal to 2d squared. And this is equation 1. And likewise, we don't know the time takes for the object 2, and also displacement for object 2 is unknown. But the idea is that since the object 2 is moving at constant actual speed, then S2 will be given as 12t. This is equation number 2. Now, from the fact that both objects, starts from the same position, reaching at the point in which one will overtake the other, they'll have to travel the same distance, no matter what. It is like you and your friend, you are here, and now you start and now you start moving towards this direction. Now the point in which the one will overtake you, that particular point, both of you have to move the same distance. That's the point of interest. So if that is the true, if that is the case, then you start to understand that S1 is the same as S2 because both objects has to travel the same distance. So what is S1? We have it as 2d squared is equal to, we have it as 12d. And from here you'll be able to solve for time. We have it as 2d squared minus 12d is equal to 0. And what is the common factor? We have it as 2d. You have d minus 6, which is equal to 0. And hence we have 2d is equal to 0, where t will be given as 0. But the time can't be 0. We'll have to ignore that one. And we'll have t minus 6 is equal to 0, where t will be given as 6 seconds. So this is the time in which both objects has to travel before they overtake each other. So that's the principle behind. So how about the distance in which both has to travel? So as it is already being expressed, both will have to travel the same distance, but what would be that distance? So we may think of substituting that one in equation 1 or equation 2 based on the interest. Hence, distance traveled by object 1 will have it as 2 times 6 to the power 2. That will be given as 36 times 2. We have it as 72. That will be given as 72 meters. That's the distance each object has to travel, 72 meters. So that's the distance each object has to travel as they overtake each other. And likewise, you can also be able to have the distance for S2. You also have it in the same way. Try that one. And what if we have this case now? What if we have, let's say, this case? And let's say object 2 is having the initial velocity given, let's say, 4 meters per second, and having the acceleration of, let's say, 12 meters per second square. Let's say we have something like that. Now, how should we have the time takes for the two objects to overtake each other as well as the distance they have to travel? So try to express that one on your own. And another application is what we call as the we call it as the lagging case, or we call it as the chasing case. So what is that one? So that is chasing, or we call it as the lagging. So lagging case, that is a lagging case. So what is that one? Let's say we have an object. Let's say this is object 1, and that is moving towards this direction. And say it is from rest where initial velocity is 0, and it is having the constant acceleration of, let's say, 10 meters per second square. And let's say ahead of it there is another object, let's say object 2, and that is moving towards this direction. And let's say it is also, now let's say it is having the initial velocity given as 2 meters per second, and having the constant acceleration of, let's say, 4 meters per second square. And let's say object 1 is behind the 2 about, let's say, 25 meters. When you object 1 overtake or catch object 2, and after, when you object 1 has to catch or overtake object 2, and after, actually, how far should object 1 has to travel to catch object 2, if that is the case. So this is what we call as the chasing, where object 1 is chasing object 2. And also call it as lagging because object 1 is behind the object 2. So since the object 1 is behind the object 2 with in terms of the actually a distance, then the lagging parameter is said to be the distance. So lagging parameter in this case, it is given as the distance. So how should you have to analyze the principles here? So do we know the time takes for the object 1 to travel? We don't know. And how about the distance object 1 has to travel? We don't know. Of course, you may be tempted to say the distance has to be this part. This distance has been covered by object 2. But as this object is to catch or overtake this one, it has to travel 25 meters and also has to travel the distance object 2 has traveled as this object was covering this distance. Now, what is the time takes for the object 2? We don't know. And how about the distance object 2 has to travel? We don't know. The distance is unknown because, of course, this 25 meters has been covered by object 2. But the reality is that this object 2 is still being in motion as this object is covering this distance. So the distance covered by object 2 is still more unknown. We don't know what is that one. But what is the displacement for the object 1? We have it as, should be, S1 is given as 5d square. That's the displacement for object 1, according to the principles behind. And how about the displacement for object 2? And since we have the initial velocity, we'll have it as, 2d plus 2d squared. And this is basically equation number 2. But you need to understand that as the object 1 is to catch or overtake object 2, first thing it has to travel or it has to cover this separation distance, and also has to cover the distance object 2 has traveled as object 1 was covering that distance. So if that is the case, then S1 will be given as the separation distance, which is 25 meters plus S2. Then we'll have what is S1, we have it as 5d square, and is equal to 25 plus 2d plus 2d square, like that. And I'll have 5d and minus 2d squared minus 2d minus 25, which is equal to 0. So what would be that one? Now we have, 3d squared So have 3d squared. So have 3d squared, and should be minus 2d minus 25, which is equal to 0. And from here you'll be able to find the time either using the factor method if it work, or the quadratic formula. And from there you'll be able to have the distance covered by object 1 and also distance covered by object 2 using the same principles. And you also have the distance traveled by, you also have the final velocity of the object 1 as it will catch or overtake object 2. You also have the final velocity for object 2 as it will be overtaken or catched by object 1. So that's the principle behind. You can also even use this actually a formula to find the distance traveled by object 1 in case you may have an interest, since you have s2 plus 25 meters is equal to s1. So keep that in mind. So this is what we call as the chasing actually case, where one object is ahead of the other in that way. Now what if we have this case? Let's say we have something about, let's say we have object 1 with initial velocity given as 2 meters per second. Let's say acceleration is given as 6 meters per second square, and let's say object 2 is moving at a constant speed of, let's say, 8 meters per second. And assuming that, let's say we should use the same separation distance as 25 meters. So what is the distance object 1 has to travel to catch or overtake object 2? And also what will be the final velocity for the object 1 as it will catch or overtake object 2? And also the time takes as well. Principle remains the same. We'll have s1 being given as 2d plus 3d squared. This is equation 1. And s2 will be given as 8t, since it is moving at a constant speed. This is equation number 2. Then we'll have s1 is equal to 25 plus s2. That is, now we have it as 2d plus 3d squared, which is equal to 25 plus 8t. Then we'll have the quadratic equation that will be given as 3d squared and plus 2d minus 8d minus 25, which is equal to 0. Hence we'll have it as 3d squared minus 6d minus 25, which is equal to 0. You'll be able to solve for time there. Then you have to substitute into this equation to have the distance for object 1 and also distance for object 2, and also the velocity of the object 1 as it overtake object 2 or catch object 2. So that's the principle behind. Now what if the separation distance is actually time? In other words, what if the lagging parameter is time? What did you say? Let's say that is the case. This is object 1 moving towards this direction, and ahead of it there is object 2, and let's say it is having as that, and let's say object 1 is behind 2 about, let's say, 10 seconds. Now the lagging parameter is given as time 10 seconds. Let's say object 1 is from rest, initial velocity 0, acceleration 10 meters per second square. And let's say object 2 is moving from rest as well, but now acceleration is given as 4 meters per second square. Now, where will object 1 catch over the object 2, if that is the case, and also when is that? So principle remains the same. S1 will be given as 5d squared. This is equation 1. To about S2, we have it as 2d squared, which is given as equation 2. But now our lagging parameter is given as a time. That's the, now we need to have to express this in terms of distance. So who have traveled this distance? Actually, who has covered these 10 seconds? The one that has covered these 10 seconds is the object 2. Hence, we should have the distance corresponding to these 10 seconds by object 2. How should we have this distance? Now, in order to find this separation distance, we substitute the time given into the displacement equation for object 2. Hence, separation distance given as the separation distance which is given as SD. Now the separation distance which is given as SD, we'll have it as, will be given as separation distance which is given as D will be given as 2 times 10 to the power 2. That is given as, should be 200 meters. By the way, this is not S2, it is separation distance. So have it as 200 meters. So which means the distance corresponding to 10 seconds is given as the 20 meters. Then from there we'll take it normal. We'll take it as normal the way we are talking about it. We'll have it as S1 is equal to 200 plus S2. Then you can be able to have the time from that point. And how about if this is the case? Let's say the lagging parameter is also the time, but now it is given as, let's say, 2 seconds. What would you say? And let's say the object ahead is, let's say, moving, is having the initial velocity, let's say, given as, let's say, 2 meters per second. Let's say that is the case, and the object 1 is having the initial velocity of, let's say, 2 meters per second as well. So what would you say about the time takes for the object 1 to catch object 2, and also the distance traveled? Principle remains the same. Have what is S1, we'll have it as 2d plus 5d squared. That is equation 1. And how about S2? We'll have it as 2d plus 2d squared. That is equation 2. And what is the separation distance given as SD? Separation distance will be obtained upon substituting time given into the displacement equation for object 2, or for the object which is on the head. So have it as 2 times 2 plus 2 times 2 to the power 2. That is given as 4 plus 8. That will be given as 12. So which means the distance corresponding to 2 seconds is given as the 12 meters. And from there you take it as normal the way we are discussing about it. And in the sense that we have it as, S1 is equal to S2 plus 12. Then you can be able to have the time takes and also distance each object has to travel before the object 1 overtake object 2. And also you can have the final velocities as well. So that's how you start to understand about the typical applications of actually equations of kinematics in a real life situations. So if you are very happy with the video, just have to subscribe to this channel so that all the videos or contents that I'll be creating will easily reach actually you. Thank you.